So my name is Franziska, and I talk about JavaScript performance, JavaScript compiler, specifically V8, because I used to be on the V8 team, and that's the compiler in Node.js and Electron, and Chrome, of course. So we'll look at performance of modern JavaScript, how it compares to performance of C++, and then very briefly where WebAssembly fits into this performance discussion. Now, why would you care about the compiler? Ideally, it's just there compiling your code, and you don't have to worry about it. And also, you really should never write code specifically for compilers to get certain performance. Obviously, this doesn't work on a browser at all because you can't control what browsers your clients are running. But even for server-side applications for Node and Electron, do not cater specifically to the compiler, because what the compiler is doing internally performance-wise is not part of the JavaScript specification. It's not in a contract in the API. It can change at any time. I mean, V8 is updated every 6 weeks, and even between those 6 weeks, there are patches and fixes. So if you have anything that you wrote because you thought it's faster if you do it this way, it can change anytime, and it's just not what you should be doing. So why would you care about learning some of the internals and the abstract concepts of modern JavaScript engines? Well, having an idea of what's going on under the hood will make you a better developer. You can think about it kind of like driving a car. Anybody can learn how to drive a car without needing to know anything about the engine. If your car is broken or for inspection, you take it somewhere and they fix it, and you just drive your car and it's all good. But if you want to be a professional race car driver or a really good driver in bad weather conditions, it will be helpful if you have some idea of what's going on under the hood in the engine. So it's a little bit similar with JavaScript. Having some idea about it doesn't mean you have to dig into it and make a big mess and then be slower the next time we push another V8 release. It just means you have a better understanding and will help you eventually when you have performance issues or when you try to figure out what's going on. Okay, so the talk is titled Speed, 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 and we're talking about performance. I want to point out I'm talking only about the runtime performance, so the runtime performance of JavaScript, C++, and WebAssembly. I'm not talking about all the other things that usually make your app slow. So I'm not talking about I/O or databases or HTTP or rendering or different frameworks. Those are usually the big things you can target when you need to improve performance. Those are also usually the things that really slow stuff down. We're just looking at how long does it take to run JavaScript code. Not sending anything over the wire, not having other bottlenecks, just the JavaScript code itself. And then a big warning, never ever blindly optimize. You'll just create a ton of bugs and make it hard to maintain your code. This should be obvious, but I want to say it anyways. Don't blindly optimize, always measure first. Make sure you even have a performance issue, make sure you have a performance issue that you want to address, and then measure and figure out where your bottleneck is. Don't just say, oh, I heard this talk, I learned some stuff about compilers, I'm going to make every function monomorphic now. No, 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 because that's going to give you such a tiny speed up, if at all, probably not even, because compilers are complicated. Don't go and optimize unless you've measured and you've figured out what you need to optimize. All right, before we can talk about performance, I want to point out one fundamental difference between a dynamically scripted language, a dynamically typed scripting language like JavaScript, and a statically typed language like C++, not a scripting language. Okay, so in JavaScript, if you want to have a property X on an object, you can do this at any time. You say, define a variable object, assign an object to it, and then set this property X to 42. Perfectly valid code. Can you do the same thing in C++? You pretty much can, except C++ compilers are a little stricter, and you first have to tell the C++ compiler what the type or the shape of object is. So you first have to define a class where you tell the compiler this class has a field that's public and it's an integer and it's called X. Okay, and then once you have this class declaration, just like in JavaScript, you can say object, object, and set the property X to 42. Nothing really special. But now in JavaScript, if you've changed your mind, if other data is coming in, you can always say, oh, I also need this Y field on my object. It has value 17. If that same change of mind happens to you in C++, Compiler is going to be like, no, 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 this is not working like this, right? So anybody who's written any C++ before, you always have to figure out what the object type is, define your class, and then you can use it. You cannot just randomly add properties or delete them like you can do in JavaScript. And because you can change the types all the time like this in JavaScript, it's called a dynamically typed language. It's not static like C++. You can change things dynamically as you need them. Say you're getting JSON over the wire and you want to put this JSON into an object. You don't have to first step say, oh, it's going to have these properties and now assign the JSON to it. No, you just take the JSON and it's dynamically creating these object types. That can be really nice when you do work with things like JSON. It's also very nice when you're just learning a language or when you're prototyping something. But for a compiler, it's a lot of work because you're not telling the compiler upfront what will happen. So in fact, if you do something simple like a property lookup in JavaScript, and obviously you do object.x all the time, like just to console.log, you're looking up the log property on console, like it's all over your code, you can't live without it. But there's a lot of things that can happen when you have this tiny little dot for property lookup in your code. What happens if you do this? You could get a type error. X could be undefined. X could be undefined on object, but be defined further up on the prototype chain. X could be a proxy with a get trap. X could have been defined with an accessor descriptor, so you have a set and a get function, which can do whatever side effects you want it to do. And even if X is defined on the object, then the compiler still doesn't know where to find the value of X in the memory layout of object, because the compiler doesn't have a blueprint of this object. If it's C++, the compiler knows, OK, object belongs to the class object, and this is the memory layout, and it's never going to change. JavaScript compiler, sadly, doesn't know a lot. So there's a lot of things that can happen for something as simple as this. And in fact, in the EcmaScript specification, so don't worry about reading all this, EcmaScript specifies how JavaScript has to be implemented, what should happen. And so just a simple property lookup is 8 steps here. Sorry. Making sure everybody's awake. So in the specification, something very simple like a property lookup is a ton of steps. And in fact, each one of those steps here is another long list of 10 steps or so. So everything's really complicated in JavaScript. It's not just, oh, you get this property and you're done. No, no, there's like lots of things. Well, if it's undefined, if it's on the prototype chain, if it's a proxy, if it's a get trap, and so on. So if like the tiniest little bit of work is a ton of work for a JavaScript compiler, what's our intuition about JavaScript performance? Is this JavaScript performance? Well, instead of intuition, let's look at some data. So I was calculating some prime numbers, and I did it in C++ and JavaScript, exactly the same algorithm. And I think this slide is super amazing. Like, yes, JavaScript is slower than C++ here, but this is a linear scale, and JavaScript is less than a factor 2 slower. Like, that's kind of the same speed, right? Like, yes, it's a little bit slower, but it's not exponentially slower or anything. You can calculate the millionth prime number, and it would take you 8 seconds with my terrible C++ algorithm. But the same terrible JavaScript algorithm only takes 15 seconds. It's not that much worse. OK, you're shaking your head. It's twice as slow, but it's actually really good. If you go back to this other slide where you think about how much work it is for a compiler to just get a property of an object, this is absolutely amazing. So how can modern JavaScript be this fast? The trick that all modern engines use is just-in-time compilation. Just-in-time compilation, sometimes called lazy compilation, often abbreviated as JIT compilation. You can turn it into a verb and say, is this code JITted? So is it just-in-time compiled? And that means JavaScript compilers only compile the code as you run them just in time. They're not compiling everything ahead of time, generating an executable that you then run. It's compiling just in time as you need to run some code. So your typical compiler toolchain, you always start with some source code, obviously, and then the compiler or the engine has a parser that is taking this human-readable source code and turns it into an abstract syntax tree, an AST. So that's a different representation of your source code that's more suitable for computers to read than the actual source code. And then the interpreter or compiler, depends on what language you talk about and the context, the interpreter or compiler then takes this abstract syntax tree and generates machine code. And you can run this machine code then. So that's your typical compiler toolchain. Now for just-in-time compilers, it's not a one-way toolchain anymore. Instead, it's a loop here where the compiler generates some machine code, a little bit of machine code is run, and then we go back and compile more code into machine code. So there's this constant alternation between compile time and runtime. So we're compiling a little bit, we're running it, and then we go back to compiling some more and running more. How is this faster? How is this a plus? This just sounds really messy and like you would have a ton of overhead for going back and forth all the time. Well, the big trick here is by running some of the code, the compiler can gather information from runtime, some runtime feedback. So this is information that the compiler doesn't see by looking at the source code or the abstract syntax tree. This is information it only gets from running the code. And then this runtime feedback is used in the next compilation step. That's the big trick why switching back and forth between compiling and runtime can actually speed up JavaScript, even though it sounds way more complicated than saying compile everything, run everything. By switching it up, the compiler can get information from runtime and use that to generate faster machine code the next time it's compiling. So JavaScript compilers, they use feedback collected at runtime to speed up the performance. Yep. Okay. And that's actually not enough to get this amazing performance where we're almost as fast as C++. Since 2011, Chrome was the first one, and then a few years later, the other major engines also added that. They all have at least 2 compilers. They have a baseline compiler, and then they have at least 1 optimizing compiler. So Safari doesn't have 1 optimizing compiler, it has 2 optimizing compilers even. And this optimizing compiler, it recompiles hot functions. So a function that is being run a lot that gets passed to the optimizing compiler. And when it compiles machine code for a hot function, it uses runtime information. It speculates that the future of inputs will be similar to what it saw in the past. So it's making a speculation about what data it will get, and it's optimizing the machine code for that. And if it turns out that the speculation was wrong, that the future is not the same as what it saw in the past, then it will just de-optimize and fall back to the baseline compiler. All right, so that was very abstract. Let's look at this more concretely with code. So I have this really complicated function here as an example. Function add takes an object, returns 1 plus the x property of this object. Everybody clear on that function, right? OK. So in our toolchain here, we have the source code, and then the parser turns this add function into an abstract syntax tree when we run the function. And now the baseline compiler generates machine code for this add function. In my example, I'm calling add a few times, and I'm always calling it with a regular object that only has a field x that has an integer value. Like it's an object, there's nothing special about the prototype chain. It doesn't have any other fields than x, and the value of x is always different numbers. It's not the same number. Like it's not always that the answer is 42, even though that's the answer to everything. It's not the same number. But it's always small integers, and it's always the same shape of an object that we're passing in to add. OK, so I'm running this function many times. So at some point, this function is considered hot because we get this feedback from the runtime, hey, this add function is being executed a lot. So the function is hot, and the optimizing compiler takes over. And it recompiles the source code for add. But now it can use the information the speculation that we will call this function always with an object that's a regular object with nothing special on the prototype chain that has an x property and nothing else. So we're speculating that the future input will look similar to the inputs in the past. And so this machine code that comes out runs much faster than the one on the left, but it only runs if the speculation is right. Now, of course, in JavaScript, it's totally legit to call a function 1,000 times with similar inputs, and then at some point change your mind and say, oops, changed my mind, I'm calling this add function with a different object now. This does not give you wrong JavaScript. It's not that your code will crash or anything. It's just for the compiler, this optimized machine code will give you the wrong result if you were to run it with this kind of input. So instead of running the optimized input, the optimized machine code, the compiler decompiles and passes on this input to the machine code that was generated by the baseline compiler. So it's the slower version, but it's correct for this kind of input. OK. And so here is actually the x86 assembly code that's being generated by V8 for this little add function that I showed you. On the left-hand side is what's generated by the baseline compiler. It runs on for a few more pages. I couldn't fit everything on here. But these 4 lines on the right-hand side is what's generated by the optimizing compiler. And this is both for the same add function. It's this add function takes an object, returns 1 plus object.x. And obviously, every instruction takes some time. So if you have lines and lines of instructions, it's way, way slower than just 4 lines of instructions. And this might look very cryptic, but it's actually not that hard, especially because we know what this little add function is doing. So if we look at these 4 lines of code there, the first line is CMP, compare. This is where we are comparing that the input matches what we were speculating. So we have this hidden class in the background in V8 where we sort of write down what an object shape looks like. And we're just comparing that the new input matches what we've seen in the past, because only for that kind of input is the optimized code right. So this is a little check or guard before we can use the optimized code. And then the next line is JN, jump. That's we are jumping bailout, so we are bailing out to the to the baseline compiler if the comparison didn't hold. So if you're trying to run the optimized code and the input didn't match the speculation that the compiler made in the beginning, if the input is not of that shape where it's just an x with an integer, then this optimized code is jumping, it's bailing out to these long list of instructions on the left. If our speculation does hold, though, then we only have 2 more lines to run. Morph is a move instruction. This is where we're moving the value of x to another register. And this is a simple move instruction because we speculated on the shape of the input, so the compiler actually knows the memory layout of it. So it's easy to access the x value. And then the last one, add. That's just addition, where we're adding 1 to that value of x. So this is how those 4 lines translate to the add function. But if you can't make that speculation in the beginning that you have a certain kind of input, then you're stuck doing several hundred instructions on the left. And as I said, doing hundreds of instructions is slower than 4 instructions. So you can actually run V8, so Node and Chrome and Electron with a flag where you say -- no optimization. And that's your upper picture. So before JavaScript engines had a second optimizing compiler, you were stuck with this upper picture, where now C++ is way faster than JavaScript. And you can't say, oh, this is amazing, we're almost at native speed. No, no, no. If you don't have the optimizing compiler, now it takes you 80 seconds instead of 10 seconds. But if you just use the optimizing compiler like the default, then you're pretty much in the same ballpark with JavaScript as with native C++. And then this slide is amazing to me because you can see the optimizing compiler in the data. So here I zoomed in to the first 200 iterations. And at first, JavaScript is a lot slower than C++, right? If you look from 0 to 50 or so, it's a lot slower. And then it actually spikes a ton, like it's not even on the graph anymore. That is where the optimizing compiler is recompiling the source code. Because obviously, recompiling something also takes time, so you don't get it for free. And that's also why we can't optimize everything all the time, because it's a trade-off between, is it worth optimizing this function? But we're calling the same function here over and over again in the prime number calculation. So it's considered hot and it is being optimized. And then around the 100th prime number, that's where you see in the data that the optimizing compiler has finished compiling and we're now running the optimized machine code. So you can literally see where's the warm-up period for the optimizing compiler, when is it done compiling, and you see that when you measure how long it takes to run it. If you want to play around with any of that, if you use Node, you can just do -- and then the V8 options, for example, trace optimization or trace de-optimization. That will list which function is being optimized and when is it being de-optimized. If you use Chrome, you just do -- JS flags equals and then use these flags. You can also print the assembly code if you want to see that. And there's like a really long list of more options. Either check the source code or like ping me on Twitter and I give it to you. There's a bunch of websites or repos that actually just list them. Okay. All right. So I was comparing JavaScript to C++, and we saw that modern JavaScript is actually pretty good compared to native C++. If you do need more speed than JavaScript, if you really do have something that's computationally intensive and you cannot deal with it, that it's twice as slow, that JavaScript is still twice as slow as C++, if you write Node or an Electron app, then you can write native add-ons. So that is code written in C++, but you use it like a JavaScript module. So users of your library don't have to worry that this is C++ code that you give them. They will just do require module, and then they'll just call whatever function they want from your API. Some popular examples that you might be using already is Node SAS or gRPC, a lot of things that work with cryptography like bcrypt, and also SQLite 3, they all use native add-ons, but when you use it, you don't need to know any C++, or you're not using the modules any different than you would use a JavaScript module. And obviously, you can use native modules in Electron. Works very similar to when you just use them in Node. And if you want to play with any native modules, we have it on the official Node.js.org documentation, the Hello World, and a few other things. And it's really not that hard to write a native module. There's two things that you need. You need a build file for JIP, a binding.jip file that gives some instructions which C++ file to use. And then in your C++ code that you have anyways for the functionality that you want to implement, you just need a little bit of boilerplate C++. Because in C++, you kind of need to wire together the function name in JavaScript to the method name in C++. Like, it's not all magic, but it's really just boilerplate code. So this is a sample build file. The important part here is that we're saying use the file primes.cc and put the output into primes. You need to give names to things, and you also need to tell the build file what are your C++ sources. And then in the C++ code, so this is my primes.cc, we have the prime number algorithm at the top. There's just a little bit of boilerplate here. So in this function here, we are wiring the JavaScript string prime to a method, so that when a user that's using your module is saying module.prime, they're getting the right method. And then the method itself, we just have to say, oh, the method is wired to our C++ function prime in the namespace prime. So this looks a little complicated. In my opinion, it's a typical copy and paste kind of situation, and then you make sure you wire your function names correctly. So yeah, you can write native C++ code and use it in Node or Electron, and anybody who's using your module doesn't need to know anything about C++, which is pretty nice. Okay. So we compared JavaScript and C++, and obviously you can write JavaScript anywhere, backend in browser, anywhere where you have a JavaScript engine. You can write native C++ add-ons when you have Node or Electron, not in the browser. Where does WebAssembly fit into this, and where does it fit in the performance story? I will say very, very little about WebAssembly because we have 2 more talks today from people who know way more about WebAssembly, so stay for those talks. Briefly, WebAssembly is a portable binary format for the web. Portable, that means you can port it from machine to machine. If you write it, it runs on Windows, Mac, and Linux. You don't have to worry about the architecture. It's a binary format. That means it's binary, so it's not for us humans. It's for the computer to read. And it's for the web. That means it runs in the browser. So it's a binary format, something that we cannot read right away, that runs in the browser, and it's supported on all platforms by multiple browsers. That's actually something really, really nice. All the big browser vendors came together and worked together on the specification, and they're still working together on the specification. And they all agreed, yes, we will implement WebAssembly according to the specification, so you can actually use it. Because there's no point of having something great in the browser if it's only supported by one browser, because then usually you can't use it for any real-life work. So it's really nice that these major companies came together and said, we work on this together. We're not doing a competition and just one person implements it. It's like, no, WebAssembly is supported in all the major browsers. Since WebAssembly is supported by V8, V8 is a Node, you can run WebAssembly in Node. And I said it's a binary format, so it's not a language it's not like you learn the WebAssembly syntax and then write WebAssembly. No, you write in your language of choice, and then you can compile almost any language to WebAssembly. So there's more and more compilers coming up. The obvious ones are C++ and Rust, but there's also Go and Java and Lua compilers and many more. All right, so what about performance? So JavaScript is still the slowest, C++ is the fastest, and WebAssembly is in the middle there, just a little bit slower than C++. And that's kind of what you would expect if you know a little bit about WebAssembly. It's not just-in-time compiled, it's statically typed, and there's just this tiny little overhead because you have to switch from C++ for calling WebAssembly. That's why it's not as fast as C++, but it's very close. So in summary, modern JavaScript is really, really fast. It's not like 20 years ago, but it's also not like 2011. That was the slide where I showed you 10 seconds versus 80 seconds. We are at less than a factor 2 for things that are computationally expensive. So unless, there's a very small amount of applications that really need this kind of performance for their computational part. So most of the time, you're probably just fine sticking with JavaScript. You don't have to worry about a different syntax. You don't have to worry about build tools, your CI. Just keep everything in JavaScript. It's almost as fast as C++, and it's probably good enough for what you're doing. If you are in these rare cases where you really need that performance, and yes, pretty much all apps should be faster, especially if you're on slow Wi-Fi, but that's not solved by changing from JavaScript to C++. It's probably because you're doing the wrong HTTP calls, or you're sending pictures that are too big, or your database is too slow. But if you do fall into this small amount of applications where your runtime performance is really, really important, then you can always, as long as it's Node or Electron and not in a browser, you can opt for native add-ons and just write it in C++. And if you do need something really fast in a browser, try out WebAssembly. But before you do any of that, make sure you measure first and don't optimize blindly. Thank you.